Hello, this is the lecture number 10. In this lecture we will discuss the Fredholm Alternative and the spectrum of compact operators. We begin with the classical Riesz Lemma, so let me write it down. Riesz Lemma first, and this is attributed to Riesz. So assume, let E be a Banach space L contained in E a proper closed subspace. So proper means simply that L is not equal to E. And then we have for every epsilon larger than 0 and smaller than 1, there exists an x naught belonging to E, satisfying the property that here we have here the norm of x naught is equal to 1, and the x naught, sorry, the distance between x naught and L is actually larger equal than 1 minus epsilon. Let's start the proof. So this proof, and since L does not equals to E, choose x belonging to E minus L, and notice that this number, call this number D, by the fact that L is a closed subspace, so put it like this, distance between x and L is strictly positive. Strictly positive. That's important, because if L is not closed, this could be not satisfied. So, by definition, and let me write it down, this distance at x and L is equal to infimum, and this is infimum x minus v, such that v belongs to L. So, for any epsilon 1 larger than epsilon larger than 0, there exists a v0 belonging to L, satisfying the property, that basically that we have here that v0 v0 minus x actually will be smaller strictly than D, and that will be 1 minus epsilon. Notice that value is definitely larger than, this is D D 1 minus epsilon is definitely larger than D. So, smaller than D epsilon. So that means it is clearly that for every there exists, yes, by the definition of the field. Very good. So, then let's conclude the proof. Then we just put 10, we put that our x naught will be just equal to, let's write it down, v naught minus x divided by the norm of v naught minus x. So we get distance between x naught L is equal to the distance, and this will be v naught minus x, and this one is v naught minus x L, and then I can continue, is equal. Still, I can pull it out. V naught minus x, distance v naught minus x L, and then you notice that delta here belongs to L, so you can write it down. This is equal actually 1 divided by v naught minus x, and then that one is just simply distance. You can write minus xl, but that one is the same as distance. This is exactly as the distance, call it d. So we put it, let's say we called it d, so this is d divided by v0 minus x, and now we go here to the formula here, call this one my star. So by my star, I have here that this one is smaller. So what is d smaller? D is smaller than, sorry, d is d, so not smaller, larger. This is larger, and then that one is equal to 1, so d is 1 minus epsilon, and here we have here just 1 minus epsilon. That's it, 1 minus epsilon. One more time. See? That one is exactly 1 minus epsilon. Good. And we're finished. That's it. We are done. This is the end. So, once we got that one, we can now formulate the Fredholm alternative. So let's say like this theorem. This is our first main theorem. We call it Fredholm alternative. I will explain why it is called alternative and why it is called Fredholm. Alternative, and underline, and again assume that E is a Banach space, and T belongs to the compact operators from E to E, so that's the abbreviation I will be using. So this is K, E, E. So that means just simply compact operator from E to itself. Then we have the statement. Then we have the following statement. Start with A. So the A tells me that in this case kernel. Maybe write it down like this. Dimension of the kernel. And this is identity minus T. Is smaller than infinity always. B, we have here that image of the identity minus T is closed, thus, once we know that this is closed, thus this image actually must be equal to the kernel of identity minus t. Oh, not fitting. Put it down. That means image of identity minus t must be equal to the kernel of identity minus t star, close it, perpendicular. And C is that this dimension of kernel identity minus t is actually equal to the dimension of the kernel of identity minus t star. So let me point a couple of things. I don't want to write it down, but maybe if you look at the point did I need? Oh, I think I forgot one. Okay, let's see. I want to put it later. So this is B is correct. Maybe I should write C. I missed it. So the kernel. So if maybe not if, just simply kernel of identity minus t is equal to 0, and this will be if and only if the image of identity minus t is equal to e, and now we put here as a d, the last one, the dimension of the kernel of identity minus t is equal to the dimension of the kernel of identity minus t star. And now the fact that this is alternative, it is related to the point C, so put it like remark, and you think about the equation that goes like this. We put it like the equation x minus t of x is equal y0. So y0 is an element from E. So you look at this equation and ask yourself a question. What does it mean, the existence? That means that there exists a solution to this equation. And what does mean unique? Unique means that if there exists a solution, it's unique. If there exists a solution, then it's unique. So this alternative tells you that basically the operator, this type of operator is either, that means that if this is either injective and surjective, or it is not. That means the solution, the existence of solution means existence is equivalent. Existence property is equivalent to the uniqueness. And we say that this is a Fredholm operator because, in fact, the kernel, as you see, the dimension of the complementing space to the image of the operator identity minus t is equal to the dimension. This is problem B. This is problem B. So here is equal to the dimension of the kernel of the identity minus t star, and in this case, that means simply that this is an operator of Fredholm index 0, which we will be discussing later if I am still able to fit it in this course. So this is existence is equal uniqueness. Basically, that's what I wanted to say, and now let's go directly to the proof. We don't have much time left. The course is almost over, so let me do the proof. So first of all, we prove A. The A is almost immediate. Notice that if, let's say like this, so if B is the unit ball, is the unit closed unit ball in, okay, put it like this, in a subspace, L contained in E, then we have that for L equal exactly the kernel of identity minus T, the T of this unit ball L is equal to the BL, so it's equal to itself. So what it is? So it means simply that this L, so notice, so that means that for every X belonging to L, we have here that, maybe I'll make it in red, that for every X belonging to L, we have here X minus Tx is equal to 0, so X is equal to Tx. So in certain way, you see this acts like identity. So now if you put here closure, but that one is actually BL, because the space is closed, because T is continuous, so identity minus T is continuous. So kernel is closed, so that's closed. And we are getting here that by assumption, T is compact, so BL is also compact, and the unit ball in a space, Banach space or no space, is compact if and only if this space is finite dimensional. So L must be finite dimensional. So let's go to the point B, which means you need to prove that we need to prove that image, we claim image identity minus T is closed. So we begin with this formula. So notice that by the fact that dimension of the kernel of identity minus T is smaller than infinity, there exists a closed subspace, and call it L, such that it is a complement to the finite dimensional subspace, topological complement. That means kernel of identity minus T plus L is equal to E, and since elements from kernel goes to 0, so we have here that T applied to L is exactly the same as the image of identity minus T is the image. Therefore, suppose that there exists a sequence, we have a sequence Xn contained in L, satisfying the property that Xn minus Txn, which I called Yn, so those are elements from the image, they converge to Y not as n goes to infinity. So let's put it like this. We claim that the sequence xn is bounded. Suppose for contradiction, maybe like this, indeed. Suppose for contradiction that xn is unbounded, then by passing to a subsequence, we may assume that this xn actually goes to infinity. So the sequence has the norm increasing to infinity. And we also have, I put here like this, Vn equals xn divided by xn. So what it is, Vn has the norm equals 1. And we have here that, and secondly, Vn minus t Vn is going to, which is, maybe write it down, which is equal y n divided by xn. It goes to 0 as n goes to infinity. So this goes to 0. Since Vn is contained in the unit ball, so this belongs to B, is bounded. Thus, T of Vn, put it like this, the sequence Vn contains, by compactness of the operator T, contains a convergent subsequence. And why? Because since T is a compact operator. So we have that T, V, and K is convergent to a certain element called this one Y naught. And therefore, since we therefore, and therefore V and K converges to the same limit as, since we write it down, and since Vn V, sorry, remove a second. Vn K minus T, V and K goes to 0, we are obtaining that V and K goes also to Y naught. And we also have here that Y naught has the norm equal 1. So by continuity, we have here that T Y naught is equal limit as K goes to infinity of T V N maybe write this just directly. Y naught minus T Y naught is equal to the limit as K goes to infinity. This will be V N K minus T V N K. and this one is equal y naught minus y naught is equal to 0. Yeah, that's by continuity. Maybe I should write it on that side. And this is a contradiction, because y0 belongs to the kernel of identity minus t, and y0 also belongs to L, which is complement of that space, and it's not 0 because the norm is equal to 1. So contradiction. So we prove it. So in such a case, therefore, the sequence, so maybe put it with 3 stars because this was just simply a justification of this claim. So that is all here to this claim. So now we can continue the proof. Therefore, the sequence xn is bounded, and again, by compactness, of t, there exists a subsequence it like this, x and k of x and such that, and here we simply have here that t, x and k is convergent. Let's call it v0 as k goes to infinity. Then we have that x and k minus tx and k, which is equal y and k, also goes to y0. Yes, let me hold it. That was the whole setting here. This is here, this is here, and then we, of course, that of course implies that x and k is convergent to x and k to y0 plus v0 coming from that, that condition here. As k goes to infinity, as k goes to infinity. So, call this value x naught, we call it, so this is by the definition, so by continuity of t, we get x naught minus t x naught is equal to 0, and this will be x and k minus tx and k goes to infinity is equal to y naught, and that proves, so the conclusion follows. So the remaining part is obvious. Once you have here that the image is closed, then you also have here the, so by the orthogonality properties, we are getting here that the image of identity minus t is the same as the kernel of identity minus t star perpendicular. So we got that one. So now, let's say we need to show that the number c, let's say like this c, we need to show if. So we need to show that, we need to show C. So let's say prove first this implication. That means if kernel of identity minus T is 0, that means that this operator is injective, then this implies that image of identity minus T is equal to E. So this is what we want to prove. So I put here question mark. So we argue, so we argue by contradiction. So let's say like this, assume for contradiction that now I denote this operator, identity minus T, which I denote by T, is injective. That means kernel is equal to 0, is injective, but its image, but E1, which I denote by that one, E1 that I denote as the image of S, is not equal to E. So that means not surjective. Of course, notice that the same argument can be repeated again. If this is not surjective, then this operator, S from E1, this goes to the S of E1, is also not surjective. It's also not surjective, E1. Because that's the whole. Sorry. I made to E1, that's the image. So this will be E1 is not surjective. It's not surjective. So we can put here that E2 is equal S of E1, and we can define En plus 1 by the definition is equal S of En, and we get a sequence of subspaces that looks like this. Here we have here E1, this contains E2, this contains E3, this contains, and it will be infinite in the case, of course, yes, in the case of finite dimensional, there's nothing to prove. So in this case, you definitely have that this space is infinite dimensional if this condition is satisfied. If we have such a claim like for contradiction, so that means this is an infinite sequence, definitely. And space must be infinite dimensional here. So it's objective is E must be infinite dimensional. Because it will contradict linear algebra. Okay, so in such a case, okay, by Riesz Lemma, there exists a sequence xn such that xn belongs to the En. Norm of xn is equal to 1, and we can also choose that here the distance between xn and En minus 1, smaller one, is always larger than 1/2. Take epsilon 1/2. So what do I do? I say, then notice that if I take the norm of Txn minus Txm, and suppose m is not equal to n, for example, m is larger than n, then what do I have here? I can rewrite it down. Maybe I should put it like this, because I need more space, and I'm not fitting it correctly. Notice that for n larger than n, we have, and I put here txn minus txn. So this will be the same as xn minus txn, and this will be minus, and this will be xn, and this one plus, so maybe put here bracket minus txn, and then plus, so what do I want to do? Xn, this will be xn minus xn. Yeah, xn. And now I say, okay, that one belongs to the en. That one, sorry. So that one, because xn belongs to the en, so remember xn belongs to the n, belongs to the en minus, sorry, plus 1. Of course. Plus 1. And that one also belongs to the en plus 1, but that one is contained in en plus 1. And that one belongs to the en, but that one is contained in the en plus 1 because we have here large. Okay, so all these elements except the last one belong to the en plus 1. So we obtained that this here, this value must be larger than 1/2. So the sequence, and I put here txn, cannot have it a convergent subsequence. So we get a contradiction. So now we need to prove the other implications. Namely, we need to prove this implication. So assume that in this case we have here that this is that okay, the image of identity minus t is equal to this whole space E, can, by the again orthogonality properties, we have here the kernel of identity minus t star is equal to the image, and this will be identity minus t perpendicular. So you are getting here that this one is 0. But in this case you also have here that the image of identity. Okay, so again, and maybe let's just simply write it down. Then the kernel of identity minus t so image identity T star will be equal to sorry. Oh, yes. Then we just prove it. Sorry. So we just prove it. So this one satisfies this property, and we can use the so we can use the implication, that one, that we just prove it, because this is the opposite. The other one was already proved, to notice that in such a case image of identity minus T star is the whole space T star. So I can continue by implication that was already proved. We have here that the image identity minus T star, remember by Schauder theorem, T star is also compact, so everything applies to the T star the same way as it applies to T, is equal to the E star. So by the orthogonality property, we also have here that the kernel of identity minus T, which is the same as image of identity minus T star perpendicular, must be equal to 0. Yep. So this is D that is left. So assume, put here D is equal to dimension of the kernel, and this will be identity minus T. And we also put here D star will be standing for dimension of the kernel of identity minus T star. So this will be two numbers. So we claim that the D star is smaller equal than D. And actually we only need to show that these two numbers are equal, because that's exactly that's exactly our claim. So we will show the one inequality, and then we'll show the second inequality, so that then this will be proving that these two numbers are equal. So assume for contradiction that D is strictly smaller than D star. So, and let me do this. So what does it mean? So that means simply that I have here the kernel. So we can consider the decomposition. So this is topological decomposition. Take here kernel and take identity minus T, and take the complementing space to the kernel, which is equal to E, and consider also the projection that is going from the E on the kernel of identity minus T, which is associated with this decomposition. That means the kernel, this is projection. So the kernel of P is exactly L, that's how it is. And since image of identity minus T is equal to the kernel, and I put here identity minus, and I put here T star bar, this is image, it follows that image identity minus T has codimension, we explained it. So it has codimension D star. It has common dimension D star. That means the dimension, that the quotient space E divided by the image, E has the dimension E finite, which is equal to D star by this particular relationship. And since we assume that, so let's say like this, so in such a case, so we have a subspace, so we have a subspace of finite dimension, call it like this, L, and I call here, maybe call this subspace M, which is contained in L, such that dimension of M is equal to D star. Sorry. We have dimension of D, maybe I put clearly, dimension of L, no, codimension, sorry. Okay. M such that, let's just simply write it down, such that image is closed, so we can write it down, image, finite dimension, so that one plus M is equal to E. So this is what I have. This one is what I have here. Now, which number was larger? So that one has dimension, this one has dimension, this one is dimension of M is equal to D star. That's the codimension. This is D star. And we have here assumptions. D is smaller than D star. So, okay, so I can define, so there exists a surjective operator, finite dimensional, which is A, and it goes from M, and it goes to L, which one is smaller? D, sorry. Mixed up things. D is smaller. Yes, D is smaller. So there exists an injective operator from, call it operator A, injective operator A, that goes from this, what is D? D is kernel. So this is kernel of identity, A from the kernel of identity minus T, and it goes exactly to N. And in such a case, so we can put, and I define the new operator, this will be equal T, and that one is equal plus, and this is AP. So this is operator, again, maybe I try to write it clearly. This is T plus AP P. So notice that this is a finite dimensional, because that's a finite dimensional. So this is a finite dimensional. So this one is compact. So that one belongs to the, so we will put it like this, from E to E. So this is from E to E. And we are getting here that S also is a compact operator. S is a compact operator. And notice also that this compact operator, kernel of the compact operator S, identity minus S is equal to 0. Indeed, just check it. So suppose here that X plus Sx is 0. So this would mean that this is X, I'm sorry, 0 is equal X minus Sx, which is equal X minus Tx minus A Px. So you can see that here this operator will be the same as X minus T, and this will be Px, and because that's the decomposition, minus, and the other one is 0, so this is equal minus A Px, and that one belongs to the image. So this one is belonging to the sorry. No, this I don't need to do it anything. This is already in the image of identity minus P. We don't need to justify. So this is image identity minus P, and that one is belonging to the image of A, which is not equal to M, and what do I see? I have here that this is direct product. So if this one is equal to 0, so this must be equal to 0, this must be equal to 0. But we are almost done. In such a case, we just also proved that in such a case, we just also proved that if this is injective, so by the previous statement, it must be also surjective. So it should be surjective, and in such a case, the surjectivity implies that the image of minus S must be equal to the whole E, but this is not true, because it was noticed here in this decomposition that here like this, X minus Sx is equal X minus Tx. This was belonging to the image of A, of identity minus T, and that one was belonging to the image of A, the second part, plus A of P of X. This was belonging to the image of A, which is not equal, contained but not equal to the M, so it cannot be surjective. So it is not surjective. So identity minus S is not surjective, thus contradiction. And so we have now that in this case we just proved that. So we have that D star is definitely smaller equal than D, but now I can just simply notice that I can apply now the same things to the second put it like this, kernel of identity minus T double star, call this one dimension D double star. So by the previous statement I have here that D, so this was smaller than D, right? So by the previous statement I have here that one is smaller equal than D star, but this one is smaller equal than D. But here that dimension is definitely larger than dimension of the kernel of identity minus T. You see, because the identity minus T in this case is a subset. Sorry, is a restriction of the operator T double star. So that means we are also getting that inequality, and we can say that the proof is completed. So this is basically the end of the proof. I'm sorry for the little, let's say, slow down. That's a long sequence of, there are lots of courses on recorded, so it becomes kind of tiring at the end. Very good. So now let's go to general definition of a spectrum. So let's say like this: spectrum of an operator of T, which is now just an operator L from E to E, from L to E to E. So let's start with a couple of notations. So first of all, notice that a bijective operator which goes like this, T from E to E, of course T belongs to L, E, E is an isomorphism. Is an isomorphism. So why it is an isomorphism? By the inverse Banach theorem, the inverse is continuous. So we can denote, we denote by the symbol, and this is a symbol that actually is standard. We go it like the GLE, and I will explain why it is called GLE and not, we could also write it down like ISO, actually for the two different spaces. If this is the set of isomorphisms from one Banach space to another Banach space, can be written ISO from E to F, but here we write GL because this isomorphism from E to E are called the general linear group. So this is called the general linear group, and that's the definition. So we start with the definition of this group. So definition of the spectrum definition. So we are doing it only for the real vector spaces. So in this case we should understand that similar definitions exist for the complex vector spaces, which we don't really need to discuss here. So let E be a Banach space, and T belongs to the LE. Then we say we put, and we put it like this. First notation is, I write it down, rho of T, and this one is set of all lambda belonging to R, such that identity times lambda minus T belongs to the general linear group of E. that in particular the inverse exists and is continuous. And we also put sigma of t, which will be equal R minus the result. That's it. This set is called the resolvent. Set, and this one is called the spectrum of t. We also denote one more set. We call this sigma p of t, and that one will be equal to the set of all lambda before, and such that we put here like this: kernel of lambda identity minus t is not equal to 0, and we will call it point spectrum. This is point spectrum of t. This is point spectrum of t. So we have couple of statements, and maybe we start with the properties. Notice this. Okay, proposition. Okay, let E be a Banach space. And T belongs to L E, then we have. First one is obvious, there's nothing to prove. If something is not injective, then it is not invertible. So that one is contained in the spectrum of T always. So spectrum, point spectrum is a part of spectrum, and B, that spectrum of T belongs to the interval, closed interval, minus T, and this will be T. And in such a case, I need to only prove B, because it is proof. So maybe put it like this for B. So that one is obvious. So to prove B, take any lambda. Take any lambda such that lambda actually is larger than the norm of that. And defined the, I don't care, this is not going to be important that this is linear or not linear, so I just put it like this: f of x by the definition, this is equal, and I put here 1 over lambda, and here we'll have here t of x minus y0 is a fixed minus x naught. So put here like this, and let y0 belongs to E be given. So for a given y0, I define, so here y0 is given arbitrary, So I look at this one and say, define this operator. So first thing I notice is that if I take f of x minus f of x prime, so what is it going to be? This is going to be 1, and I put here like this. What is this x? This is still x. This is dot. So this is equal lambda, and I put here like this, tx minus y naught minus x, and this is minus, put it like underline, minus, and I put here like this. So this is again minus 1 over lambda, this will be tx prime minus y naught, and minus x prime, yes, and what do I get here? I'm getting here, okay, I screwed up, sorry. It's much simpler. I should concentrate. We need to show that first one, A, that this operator, call this operator S, lambda identity minus T, is injective, and B, S is equal lambda identity minus T is surjective. So start for A, maybe this is not good, I and double I. That S, by the definition, lambda identity minus identity. So not everything is going to be identity minus T is number 1 injective, number 2 surjective. To number I, we just need to show that if you take lambda, suppose x different than 0, maybe write it down like this. Suppose that s of x is equal to 0, so this will be the same as lambda x is equal to t of x is different than 0 for simplicity, and then that one will be equal to lambda is equal to t of x divided by x, and that one what you are getting here, that this one is smaller equal than the norm of t, so that means lambda is, so that's a contradiction with the assumption that we made here. So that's not possible. So that means S is injective. And to prove second one, I just put here f of x is equal 1 over lambda, and this is tx why I put here linear operator, so this will be again another s 1 over lambda, and this will be tx okay, we need to show that this operator, right? Lambda identity minus t is surjective. That means for every y not belonging to E, the equation written like this, lambda x minus tx equals y0 has a solution. But this equation can be written differently. Namely, you have here like this: t of x plus y naught is equal to lambda x. And now we assume that lambda is larger than 0. Sorry, that lambda is not equal to 0 because it's larger than the norm. So that means this one is equivalent and this one is equivalent, that 1 over lambda of t of x plus y0 is equal to 0. Put f of x is equal to 1 over lambda tx plus y naught, and notice that, and here we have here f of x minus f of x prime is smaller equal, and this is easy to notice, 1 over lambda absolute value, and here we have here t of x minus t of x prime, which is smaller equal norm of t divided by lambda, and this is x minus x prime. So f is Banach contraction, is a Banach contraction, is a Banach contraction. So there exists a unique fixed point x, and that means in particular we solve this equation, which means is surjective. Means it's surjective here. So we're done. So now we need to formulate the last result, namely, and this is the result. So let's select this theorem. This is important. And that's a spectrum of compact operators. So let E be a Banach space. Let E be a Banach space, and assume that T is a compact operator on this Banach space. Then we have one second. Then we have maybe like this, the following points. So A, that then we have an infinite dimension. Of course we are forgetting something. An infinite dimensional Banach space, and T belongs to the compact operators. And then we have the following. 10. First statement, A, 0 is always in the spectrum of T, and that means T is never isomorphism. And then you have here B. B is like this. for every lambda. So put it like this. So sigma of t minus 0 is contained in the point spectrum. So that means this spectrum is composed of eigenvalues, and in particular, if lambda belongs to the point spectrum of P of t, then this implies maybe like this. If this belongs to the t minus 0, then we also have here the dimension of the kernel of this lambda identity minus t is kernel lambda identity minus t is finite dimensional, and then we have here C, and then in this C we have the following, that if that sigma of t minus 0 is either we have the one of the following possibilities. We have one of the following possibilities, and this is I. This one, sigma of t, so is either equal 0. The second possibility is that sigma of t minus 0 is finite. So that means can be composed of finitely many eigenvalues. And then we have here number 3, and that's the one that actually needs to be proved, is an infinite sequence composed, so sequence like this, call this like this, lambda n, such that lambda n is convergent to 0. So we have here that the sigma of t minus 0 is just a sequence convergent to 0. So proof, we will be able to achieve it in short time. So notice that statement A that is always true. Why? Because the T cannot be isomorphic because it's compact. So if the space is infinite dimensional, then it will take the ball, the unit ball, the image of the unit ball would be a neighborhood of a 0. And since this is a neighborhood, it contains the ball, and the ball cannot be compact in infinite dimensional spaces. So this is a contradiction, because T of B is compact, is relatively compact. So that means every subset of T of B is relatively compact. So in order to prove B, so of course it is clear that if you have here, that we have here Fredholm alternative for B, notice the following. So assume that lambda is not equal to 0, then you have here the lambda identity minus t. Do you see this is the same as 1 over lambda, and this is identity minus, other way, lambda, and this is identity minus 1 over lambda t, and here this is a t, this is a compact operator, this belongs to the compact operators k of e. So this operator, if it's not an isomorphism, by the Fredholm alternative, it has a kernel. This operator has a kernel, but this is the same kernel as that operator. That means this kernel is actually the eigenspace of the operator t. And in such a case, we also prove that this kernel is finite dimensional, so this portion of the proof is definitely finished. So, of course, if you look at the point C, so if not 1, then maybe B, and if not B, then C. So only the third possibility is needed, that needs to be proved. And in order to prove the third possibility, suppose that there is a sequence. So you have here sequence lambda n of eigenvalues. So this is sequence of eigenvalues. And we assume that these eigenvalues converge to alpha 0. And of course, if you have here eigenvalues, then you have here eigenvectors. So let's say like this, we have here eigenvectors. So En corresponding to lambda n eigenvector. And of course, in such a case, we assume that these eigenvectors and eigenvectors are linearly independent for different eigenvalues. So we can put it like this. En, by the definition, it will be span, and this will be span E1, E2, En, and then we just simply look at this particular subspaces. Those are finite subspaces, and notice that if I take T minus lambda n, and this will be identity, then this operator will take this subspace En into the subspace lower En minus 1. Why? Because here the last vectors will be nullified. This is eigenvector for lambda n, so it will be nullified. So it goes to the smaller subspace. So what do we do the next? We apply the Riesz Lemma. So I don't have enough space, so let's say like this, try to fit it. I'll try to. By Riesz Lemma, we choose the xn belonging to En. Xn is of course norm equals to 1. And we have here the distance between xn and En minus 1 is larger or equal than 1/2. Okay, so now look at this particular expression. I take like this. Take Txn divided by lambda n minus Txm divided by lambda n. And rewrite it down like that. So I write it down like this. This is Txn minus lambda n xn divided by lambda n minus Txm, and this one is minus lambda m xm divided by lambda n. And now something is, you see, this cancels, so I have to put here like this, plus xn minus xm minus xn. And suppose m is larger than n, so those are not the same thing, those are not equal. So these two things are larger. So what do I see here? I see here that that one belongs to the that one belongs to the En minus 1. That one belongs to the Em minus 1. This one belongs to the En. And this one belongs to the En. And En minus 1 is containing all of them. En, sorry, this is increasing. Sorry, increasing. 1 second. The largest one is En. Very good. So So we have here x m belongs to the em, and then x all the others. So this is all the others. So notice that em minus 1 contains en, and that also contains, and it's also containing n minus 1, also containing em minus 1. Wow, so that means everything, that portion, this, including that vectors here, this belongs to the em minus 1. And now you can write with the confidence larger equal than 1/2. So now, if lambda 0 means this, if L converges to the lambda 0, so it's a sequence, converges somewhere else, you can see here that by the convergence you will be getting here that a thing that there's a contradiction. So this, you will be getting here that this is not possible. This is not possible because you will be obtaining that the sequence 10, the sequence Txn divided by lambda n has no convergent subsequence. So we are getting contradiction. Why? Because this is a bounded sequence. This is a bounded sequence. Okay. Since xn lambda n is bounded. Since we are getting contradiction, so this one is lambda 0 not equal to 0, notice. So lambda 0 must be equal to 0. So lambda 0 must be equal. Okay? So if this lambda 0 is not equal to 0, then that sequence cannot have a convergent subsequence. Yep. Good. And that's the end. I think we will not cover the Fredholm operators, so please read about it. Thank you.